Hey guys, welcome back. Day 12, Quantum Mechanics. Today our goal is to understand how electrons are arranged in atoms and how to use that information to predict atom behavior, or the behavior of atoms. Right? We want to study the electron and understand what's going on. So we know matter is composed of tiny particles called atoms, and atoms are composed of even smaller particles. We know protons, neutrons, and electrons. Quantum mechanics is the study of these atomic and subatomic particles. Now, the math required for quantum mechanics is very advanced and way beyond the scope of this course. However, we do not need to do that math to talk about the results, just like I don't need to be able to rebuild an automatic transmission to drive my car. Right? I can just drive my car. So the goal of this lesson is to tell us the findings about that electron. And why do we care about electrons so much? Because electrons' behavior determines much of the atom's behavior. Right? The problem arises that when we study electrons, that the electrons are incredibly small. Right? We have approximate mass of 9.11 times 10 to the negative 31st kilograms. An unknown size. We don't really know the radius of it. It could be a few centimeters smaller. We don't know. We don't even know how big the thing is. Right? We know it exists. We don't know how big it is. And this is why direct observation of the electrons in the atom is near impossible. Right? Because observing the electron changes its behavior. Even shining light on the electron affects the electron, right? Which we'll get to in a second. Quantum mechanics is a mathematical model that describes the predictability of behavior, in this case we're talking about electrons, and allows us to build up a system to predict electron behavior. This predictability on how electrons are arranged in atoms allows us to predict atom behavior as well, such as why sodium loses one electron to become positive. Right? We've talked about sodium's plus one. Well, we're going to learn why. Okay, so let's look at what we have here. Right, and so if we actually go to electron behavior, all right, what we expect is electrons shoot a bunch of electrons. The ones that are going through the slits will be bright on the slits and then be dark everywhere else. You just see two lines of electrons hitting the slits. Problem is electrons diffract, and they interfere with each other, and they make this pattern. So, can an electron be a wave? Can an electron be a particle? The answer is yes. It goes back to this picture of Schrodinger's cat. All right. So let's look about what we have, and we have to again do some qualitative pictures here. All right. All right. With light. So let's talk about the Bohr model. All right. You have an electron. I have an electron sitting down here. Whatever shape, size that electron is, there it is. All right. So energy of the orbits. So if you think of the orbits of the planets, right? Mercury, Venus, Earth, Mars, etc., right? You know the planets. They've changed the planets since I've been in school. It used to be 9 planets. Now there's who knows how many planets. All right? 9, right? We had 9 planets. All right, but the first one was Mercury, then Venus, then Earth, then Mars, right? I understand Pluto's moon and Pluto itself are about the same size. That's why, and they don't have they don't orbit around one of them. So I understand the physics behind it. But I think there were 9 planets when I was in school. Well, here we got energy levels, and it's kind of like the orbits of the planet. So they thought, Bohr thought, N1 was the first orbit, N2 is the second orbit, N3 third orbit, and it's not quite like that, but for our purposes, we're going to look at this for these energy levels. The energy levels are sequential. And so if I throw in some light here, and get some energy coming in as h nu as a photon, right? Okay, no matter what happens, because if we talked about this, the hydrogen atom, it's going around, the electron's going around trillions of times in a second. So no matter how light hits this atom, it's touching the electron, this photon, this wave packet, right? Kind of a particle or a piece of light is going to hit this electron, and that electron is going to be excited, right? And it can go up to an excited state here. All right, so some definitions. I have ground state, which is the lowest energy state. So the lowest energy state. So if this is a 1 electron atom, n equals 1 is the lowest. All right, and this will make more sense in a little bit. And this would be an excited state, because it's got more energy. It's excited. Okay. The electron, there's several different ways for the electron to release energy, right? So the energy that came in, all right, this energy here is the difference between the energy there too, by the way. All right, and then what happens is if this electron comes down to here, right, we see E equals h nu, a photon, right, which is light, is emitted back. So the energy leaves as light. And a crude analogy of this is, kids, sometimes even adults, right, because sometimes it doesn't change. I'm sure we've all been in a spot where we had some type of string, cord, rope, toy, right? Had some type of string that we would swing around our head. And a small radius versus a big radius. The smaller the radius, the slower you can go. The bigger the radius, the faster you can go, right? And so when I need my radius bigger, if I'm swirling something over my head, it's got to go faster, right? Okay, and you got yelled at for doing this, I'm sure, because you're going to break something or hit somebody, and sure enough, we didn't listen, and something broke or somebody got hit. There was tears, and it was a bad day because we didn't listen. Well, the electron, when it goes from a lower energy level to a higher energy level, it needs more energy to get up there. Just like you need to swing your rope faster around your head. All right? And then when that electrons come back down, it can actually lose some of the energy, and that's what we see as an emission. Right? So this first button, this first arrow right here, this arrow where the photon comes in, hits the electron, we call that an absorption of energy. That's an absorption, and obviously this is an emission. All right? So again, this is a qualitative diagram. It's not exactly what we're seeing, right? But it's a qualitative diagram. And so if we look at the hydrogen atom now, here's the Bohr model from the book. All right, try to get it all on one screen here. Okay, there's the Bohr model. And so these were the emissions from n equals 3, 4, 5, and 6 to n equals 2. Right, just to n equals 2. All right, so 3 to 2, 4 to 2, 5 to 2, and 6 to 2. And we see those lines, and we can actually observe. So I want to point something out. This is what we observe. We observe those lines. Okay, that's, our eyes can see that. All right, so this is our theory, what's going on, trying to explain that behavior. Now, qualitatively, here's all the hydrogen atoms. Again, the ones we can see the visible. We can still observe the infrared and the ultraviolets. We just can't do it with our eyes. We have to use some type of other detection. Right? Just like, night vision or thermal optics, right? There are ways to see things that we can't see with our eyes, and same thing here. Right? So we got ionization, is where the electron, if I had an electron here, this electron leaves. It says leaves. The electron's gone. But the excitation, I can go all the way up to n equals 6, maybe even 7. And there's infrared ones, there's the visible, right? The ultraviolet, they all exist, because there's a big gap from n equals 1 to n equals 2. Okay? And so these are the electron, or the hydrogen atom, and we know, again, what we know is that E equals hc over lambda. Energy is equal to constants, some numbers, over the color. Right? So as all these colors have different energies, right? Each of those wavelengths, different energy, right? Because, again, remember, C equals lambda nu, and E equals h nu. All right, so we know that each of these colors, wavelengths, has a frequency, and each frequency has an energy. That's where we get this equation from. All right, so now, orbitals. We talked about how fast these electrons are going around, trillions of times a second, right? Where they're at. And your author, Tro, does a good job about probability. All right, where r is the radius where all these electrons are. So if you could take pictures, let's say we could take pictures of the electron. We can't. Let's say we could. Let's say we could just take a picture where it is. Camera, right? And you would just do it, and it would actually get where the electron is. And so if you would take pictures, the time-lapse video, picture every, I don't know, femtosecond for a couple hours, you would get this pattern of where the electron is, right? It's not following a fixed orbit, but it's going to be here, it's going to be there, right? It's going to be somewhere in this region. You're not going to find the electron out here outside of the radius. It's not going to be there. That's not where it's going to be. They're all going to be inside these blue dots, right? And so the probability, obviously at the nucleus it's 0, but there's a probability, which we call psi squared, of where the electron is going to be. All right, and as we get further and further out, that probability goes way down to almost 0. All right. Okay, so 1s. So here's our orbitals. Here's S, and we'll talk about where these come from. S is a sphere, because that's the probability. All right, so we just call it a sphere. P's, all right, look like this. There's a P on the x-axis. So, again, three-dimensional. And I think if we draw, there's a three-dimensional, X, Y, Z here. See how that works? All right. So that dotted one's coming in and out of the board. That's usually Y. So, oh no, usually usually Y. Z is vertical. Now, X is here, and then Y is in and out of the board. That's just how they work it. All right. Okay, and so everything, they're all 90 degrees. Okay. Again, if I draw that again, all right, you can see how I can change the Y depending on how big or small, but they're always 90 degrees from each other. Okay. All right, those are the p orbitals, and these are the two sets of orbitals, S and P's, that we'll really focus with. There's D's. There's 5 d orbitals, and we'll explain those more in detail. But D on the x or the yz plane, D on the xy plane, D on the xz plane, dx squared minus y squared, which are on these 4 axes, the x and y axis, and then dz squared, which looks like a p orbital with a donut. All right, and then it gets even more fun with the f orbitals. Those are the orbitals, which, great. All right, so let's review our quantum numbers. All right, so the wave function, psi, all right, wave function, all right, is characterized by 3 numbers. There's going to be a 4th number, too. So, symbol, right, name, values, significance. All right, so the first one is N, right, and that's the principal. That's the principal energy level. All right. This is our values. N can be 0, 1, 2, 3, all the way technically to infinity. All right. It's a mathematical model. This is our energy of the orbital. Okay. So it's the total number of nodes plus 1. Okay. That might not make a lot of sense to us, but that's okay. It's the energy. All right. Then there is the secondary L. And L is anything 0, 1, 2, 3, all the way up to n minus 1, whatever n minus 1 is. Right? It's our shape of orbital. Right? It's the number of planar nodes. Okay. Then there's the magnetic M sub L. And M sub L equals negative L through 0 through positive L. And this gives us our orientation of the orbital, right? Which is the orientation of the planar nodes. Okay. All right. Now, last but not least, there is the MS, which is spin. And MS can either be plus 1/2, which we call up, or minus 1/2, which we call down. And that's the spin of the electron. All right, that's the electron spin. All right, spin of the electron. Now, it affects, it's just a property of the electron. It's an electron property. It, in effect, it doubles the degeneracy, and that means the same energy level, the same energy. So it doubles the degeneracy of each energy level. Means we can put 2 electrons into each orbital, not just 1, which is good. Now, of course, it's a non-classical property. So it's not like a baseball spinning one way or the other, right? Those of you who played baseball or softball, pitchers will put a spin on the ball to move the ball to help make the ball curve one direction or another. This is not what we're talking about, but you can think of it this way because we can't think of it any other way. But you can think of it spinning one way or another. Now, how do you know it's spinning? Right? Do we just make this up? Not really, because a spinning charge produces a magnetic field. And these electrons, spin up electrons, will react differently than a spin down electron. The thing with the electron spin, all right, is we don't know. No, we do know. We know that the electron spin can change. Electrons can flip their spin. So we just arbitrarily assign the spin, and it has to be measured, but then it can change. So that's where we're at there. All right, so let's look at this. Let's look at, if I have n equals 1, n is 1. What is L? L can only be 0. All right. All right. And now we're going to learn, and I didn't write this there, L has some letters instead of numbers. So L equals 0, 1, 2, 3. Okay, this is the orbitals. S, P, D, F. So if L is 0, we are in an S orbital. If L is 1, it's a P orbital. If L is 2, it's a D orbital. L is 3, it's an F. If I go back to my energy level 1, I only have one option for L, right? Because again, this is a mathematical model. So if N is 1, there's only one allowed value for L. Kind of like if I have $100, I cannot buy a $200 item. It's not allowed, right? Assuming, no credit cards or nothing, right? So if I have $100, I'm not buying a $200 item. I can buy a $50 item, can't buy a $200 item. All right. So if N is 1, L can only be 0. That's it. All right, which means there's only one overall orbital. All right. And of course, M sub L is just 0. Negative L to positive L. There's only one orientation of that one orbital, and that's why it's an S orbital. So if we go back and look at these orbitals here, it's a sphere, right? It comes from this probability density distribution, but it's a sphere. How many ways can you orientate a sphere? It's just one, or I guess infinite. So one, right? One orientation. If N is 2, right? N is 2, L can be 0 or L can be 1. M sub L can be 0 there, but M sub L can be negative 1, 0, or 1. All right. So that means I have a total of 4 orbitals for N equals 2. Right? I have an S and P's. I have 3 P's, 1 S. Okay. All right. Well, each of these orientations represents a different orbital because each orbital has its own orientation. So what are the orbitals? That's a great question. And here I just have 1s. That's it. That's my orbital. It's a 1s sphere. Here I would have 2s, and then I'd have 2p, and then on the x, 2py and 2pz. I would have 3 2p's. All right. So I have a total of 4 orbitals. Now, if n equals 3, L can be 0, L can be 1, L can be 2. ML, if L is 0, ML is 0. If L is 1, M sub L could be negative 1, 0, or 1. If L is 2, M sub L can be negative 2, negative 1, 0, 1, 2. Alright, so if L is 0 and is 3, that would be a 3s orbital. If L is 1, right, I'd have 3px, 3py, and 3pz. We pretty much just call them 3p. We'll lump all of these into just saying 3p orbitals. Just like we bump all those and saying we just got 2p. And then we have the 3d orbitals. Now that's 3dxy, 3dyz, 3dxz, 3dx squared minus y squared, and 3d squared. Z squared, 3dz squared. There we go. But we're just going to throw on these. And there's 9 orbitals. So you might be seeing the pattern here. Right? Okay. So N is the different types of orbitals. N equals the different types of different types of orbitals. So if n is 1, I only have one orbital. If n is 2, I have two orbitals. 3 orbitals. 4 orbitals. All right. N squared equals the total number of orbitals within the principal energy level. So the total number of orbitals within a principal energy level. All right. And then we have 2L plus 1. And that equals the orbital degeneracy. Which is the number of orbitals in a set. All right, so if L is 1, 2 times 1 plus 2, or sorry, 2 times 1 plus 1 would be 3. 3 orbitals, 3 p's. All right, if L is 2, 2 times 2 is 4 plus 1, 5. 5 orbitals. If L is 0, I have 1 orbital. All right. So now what we can do with this math is can build up, right, the electron configuration of any element by placing the electrons in successive energy levels until the atomic number is reached. Okay, we can do this. 3 principles. Okay. The first one's from Bohr. It's the off-ball principle. And this one says we fill orbitals in order of increasing energy. All right, so we fill them in order of increasing energy, and we're going to learn this goes right with the periodic table, which is fabulous. Then we got 2 from Pauli, and this is the exclusion principle. And the exclusion principle is that only 2 electrons in each orbital with opposite spin. So there's 2 electrons in each orbital with opposite spin. And 3, Hun. A lot of times we call it Hund's rule. Right? We call it Hund's rule, but this is maximum multiplicity. Maximum multiplicity. And this one says that as far as possible, right, keep the electron spin the same electron spin the same, right, which is parallel, right, in a degenerate set of orbitals. Alright, so we got the three principles, and then we can build up the electron configuration following these principles and N, L, M sub L, and SMS. And so we are going to start that in a second.